Hi, so welcome back to the live streaming today. So today we are fortunate and happy to have you once again here. So today we want to look at quantitative methods for business, but our focus is going to be centered on calculus generally as the discussion for today. So if today is your first time on the channel here, do want to subscribe, like the video and share so that others will get a benefit to always to join us in that particular case. So let's begin right away so that we get things started in that particular case. All right, so let's flow for today. Let me bring up my screen so we get started that line. All right, so let me share my screen. So we go. All right, so we're about to start the discussion going. So we are going to look at calculus generally in the lens of business perspective. So that is what we're going to discuss today. So let's stay focused. If you have any questions, feel free to drop in the comment section. Also bring it up and explain concept that you don't understand so that going forward you appreciate the course better that particular case. All right, so let's begin right away so that we just have to flow, no time to waste. So the concept, calculus, possibly or clearly differentiation generally. So we are looking at differentiation. We are looking at differentiation generally as one of the branches under calculus. All right. So when we talk about differentiation straight up, one key that we need to take notes as a general understanding is that differentiation, you're talking about changing something. So differentiation, so definition. So once you hear of differentiation, you're talking about change in something. That is the first thing that we need to have generally. When we talk about differentiation, we are talking about change in what in something generally at the end of the day. Okay, so what is then the change in something that we are trying to talk about, trying to explain generally here? So the goal here is that when we are talking about change in something, the change in something here can be in relation to business. It can be as a result of two things. Either there is change in what? The efficiency. So we're talking about what? The efficiency or the effectiveness. Efficiency or effectiveness or the delivery system that exists within the organization. Efficiency and effectiveness, or effectiveness and efficiency in the delivery system in terms of service provision, or service, yeah, let's say service provision or service provision generally. Okay, or it can also be as a result of possibly a change in production, a change in production, a change in production, right? So the change in production can also be as a result of changing, let's say, raw materials, raw materials. We talk about what? Work in progress, work in progress, and can also talk about finished output or the finished product, the finished output or the finished work product, or basically the product we sell or the product we sell generally at the end of the day. So if there's a change in efficiency, effectiveness, or delivery system of the organization or their service provision, and as well a change in production that can be as a result of changing raw materials, our work in progress, finished goods, our systems and strategies that we use as an organization. Now, if there is a change in these qualitative factors we are trying to talk about or we are discussing here, then you ask yourself, in which aspect of human resource, as a human resource, in which aspect of resources can we actually attribute these changes to, right? So that is what I'm saying, that if there is a change in this aspect, which aspect of the organization in terms of resource can we relate this change to? So you realize that when it comes to changing efficiency or effectiveness or service delivery or provision, it has a relation with what? Human resources. Very important, human resources. So you're talking about human resource within the organization, the human resource within the organization. And as well, a change in production, raw materials, work in progress, or finished output can be as a result of what? Our natural resources that we use within the organization. Because it is out of the natural resource that we process into what? Work in progress and finished output generally at the end of the day. So if there is a change in these qualitative variable in relation to human resources, in relation to natural resources, then how do we get to know that there has been a change in their effectiveness, in their efficiency, in their service delivery within the organization, or there has been a change in raw materials, work in progress, or finished output? How is that possible? How do we get to know? Okay, so if that is the case, then differentiation as a mathematics model will help us or will provide us with mathematical tools, right, that can help us to know the change in this what aspect that we are trying to talk about. So generally, all that we go, the mathematics model here will help us. Yes, it will able to help us to assign what numerical scores to these qualitative variables. So now let's say the change in the human resource as a result of the effectiveness or service delivery within the organization. Let's say let's assign what a variable to it or a number to it. Let's say we assign a variable to the change, and now this change, the variable we assign to it should be what? Y. So you ask yourself if the variable y should change, which represents what? The change in the qualitative what variables that we have discussed: effectiveness, efficiency, service delivery system, and provision. I mean, if there is a change in this, what are some of the factors that can also affect these qualitative variables we talk about? So efficiency or effectiveness, one of the key things that can affect this aspect of human resource can be one. It can be possibly as a result of what? Quality management. So let me represent, let's say, quality management by, let's say, X square. Quality management, generally quality management. That is one aspect that can affect the efficiency and effectiveness of what? Human resource, quality management. Let's say too, the jurisdiction that a business will operate, it gives them a competitive advantage, and so therefore workers are motivated to work extra harder, and so that will going to result in the change in their service delivery within the organization, right? So let me put in just in simple way, motivation. So let's say the motivation factor here is, say, X. That is fine. Let's come back to our production, which is as a result of the natural resource that we have generally at the end of the day here. Okay, so if there's also a change in our raw materials, our work in progress, our finished goods, let's say we want to represent that change by the same variable that we use for the human resource. Let's say what? Y. So what are some of the things that can influence what? Our raw materials change, work in progress, finished output, possibly raw materials in terms of, let's say, stocking, whether over stock or under stock. It can be as a result of, let's say, our supply chain system. Let's say there is a change in our supply chain system. So let's say the change in supply chain system can affect what? How we procure raw material. So let's say that change, let me present that one as what? Let's say what? SQ, as a change in what? Our supply system in terms of procurement. And let's say finished goods. A change in finished goods or the product that we sell can also be as a result of possibly advertisement costs, or less advertising, promotion. Those one can also affect what? How our product, I mean, actually sells in the market, right? So advertisement, let's say that one is also, like, say, S square, and other related what variables coming in. So once we're able to quantify this qualitative variable into numbers or variables, then we can then explain that if there's a change in any of these variables, then we know that it's actually coming from, let's say, whether efficiency, let's say whether our finished product, let's say raw materials, or those issues, right? So that is what differentiation or calculus provide us with the basis to actually help us to understand. So now, if that is the case, now we can start with our discussion, calculus. So, or differentiation generally. So when we talk about differentiation, we are saying that differentiation has to do with what? The process of what? Or a change in what? A function, right? A change in what? Function. And this function that we are talking about can either be a derived function and derived coefficient. The process of finding the derivative of what? A function. The same thing as a change. But before we hit on that, let's get this right too. When it comes to these variables and in a functional related form, mostly in most cases or most issues or in most cases we represent what? The y as what? The dependent variable. The dependent what? Variable. Okay. We represent y as a dependent variable, or you can also call it as what? F of x. F of x in terms of representation, f of x. All right, and then the x values to are also represent as what? The independent what? Variable. The independent variable. The independent what? Variable. The independent variable. Okay, so if you have dependent variable and then independent what? Variable. Okay, so if that is the case, and we have established that differentiation generally in terms of the definition, when we talk about differentiation, we are saying that it is a process of what? Finding the derivative. So that's a proper definition. The process of finding the derivative of a function. The process of finding the derivative of a function. And this derivative can also be called a derived function. So the derivative of a function can also be called what? Its derived function. So a derived function and derived coefficient. Derived coefficient. And I will explain that in a moment. Okay. So derived function, it derive coefficient generally at the end of the day. Derived function, it derive coefficient generally at the end of the day. So if that is the case, then let's see. If that is the case, then let's see. We have derived function, derived what? Coefficient. So now from our discussion from this equation that we're able to form from these changes in the qualitative variables of our resource that we have in the organization, once you are able to get the definition that now is a process of finding the derivative of a function, and this derivative can be as a result of a derived function and derived coefficient, then we can then start with our rules or the basic notations for differentiating what? A function. So let's talk about the rules of differentiation. From there, I will come back and explain the derived function and derived coefficient generally at the end of the day. So let's take note of that. Okay, so if that is the case, now let's say we start with our rules. So rules of differentiation. So rules of differentiation. Rules of differentiation. Okay, so let's go. So rule number one. So I'm going to use the initials R1. So once you see R1, I mean rule number what? 1. So rule number 1, we are going to talk about what? The power rule or the power law. So the power law or the power rule. Actually, it is actually this rule that set the tone of what? Differentiation. It is a basic rule that set the tone for differentiation. So let's flow. So now this rule is saying that, okay, so if I have a function in this form, we call the power law or the exponent what law or the exponent what rule. It is saying that if I have what a function, say y, to be equal to what, let's say x, okay, to the power n. In our discussion, we are going to make use of y and x. Now you know that y is what a dependent variable and x is what an independent variable. I hope now you know that. Okay, so if that is the case, that the power law is saying that if I have a function y is equal to x to the power n, this is how the differentiation goes. Now I want to differentiate what y with respect to what x. So the goal here is that when I differentiate y, it's going to be what? Differentiate y, differentiate what? X. So the differential of y is going to be what? Differentiate y, differentiate x. I hope you can see that. Assuming we were using what? A different independent variable, let's say here to be, let's say, v. That would have been differentiate y, differentiate what? V. So now enough of the talk. So let's put action here. So I can say that the differential of this is going to be what? Differentiate y, differentiate x. That's going to differential of what? Y. And that should be equal to. Now we come back to the independent variable aspect or the part. So what is happening here? Once we differentiate x to the power n, all that we'll do is always make sure that the power come in front of the x and multiply the coefficient of the x. So the power will actually multiply the coefficient of what? The x in front of the x here. So it's going to what? N. And we know the coefficient of x here is 1. So n multiplying 1. And once you are done, that is the differential of the power. And the next thing you want to do is to repeat what? The independent variable x or any independent variable going to be given in the question together with the power. So you just have to repeat it. So x to the power n. Once you repeat that, that's the second step. And the last thing we want to do is to subtract what? 1 from the power. So we will therefore say that our dy over dx is going to give us what? N x n minus 1. And this becomes the basic rule for differentiation to differentiate all basic functions generally at the end of the day. So let's take note of that. Let's take note of that. Let's take note of that. Okay. So if that is the case, then that is the first rule, rule number 1. Let's take an example to make meaning out of what we are trying to actually explain generally at the end of the day here. So example. Let's say we have a function y to be equal to x to the power 7. X to the power 7. How we are asked to find out dy over dx. Then dy over dx is equal to question mark here. Okay. So let's see how it flows or how it goes. So generally we said that differential of what? Y is going to be dy over dx. So we have our solution here. So let's see how it goes. So it's going to be what? Y to be equal to x to the power 7. So differential of y is going to give us what? Differentiate y, differentiate what? X. Differentiate y, differentiate x. And that should give us, so now we come to the power, the differential of the power. So the 7 will come and multiply the coefficient of x here, which is what? 1. So we have 7 multiplying 1 here, and repeat the whole of what? The independent variable x and then the power. So it becomes x to the power 7. And the last thing we're going to do is to subtract what? 1 from the 7. So therefore, we'll say that dy over dx is going to give us what? 7x to the power 6 at the end of the day. So that is the first thing that we need to when it comes to what? The rules. We can also be given, let's say, another one. Let's say we have what? Y to be equal to, let's say, 3a to the power 3. We are asked to differentiate this. Remember now, we are differentiating y with respect to what? A and not x. So you tell us that here should be what? Differentiate y, differentiate a should be equal to. So the power 3 will come and multiply the coefficient of 3 here. So it becomes what? 3 multiplying 3. Okay. 3 multiplying 3, and then we repeat the whole of what? The independent variable a cube. So repeat it, a to the power cube and then we subtract what? 1 from the independent, which is what? 3. So we subtract 1 from the exponent 3. And then we have what? dy differentiate y differentiate a to be equal to 9a squared. And we are done generally at the end of the day. So this is the issue about what the power law that we need to understand generally at the end of the day. If you have any question, you can drop in the chat box that I will bring you up and we'll explain the concept for you to understand better. If you just join us, thank you for joining us, but do all to share the video and like it as well in that particular case. All right. So now let's move on. Sorry. Hello? Hope you can hear me. Hello? All right. So that is fine. That is fine. So I was talking about differential of a constant function that when we talk about a constant function, the constant function is a function in which the independent variable is a number. So the differential of any constant we're going to result to what? 0. And that's what we were trying to establish. But I think something went up. So just have to correct that to suit it. Then at the end of the day. Okay. So what is then happening here? So we want to differentiate y to the power, y is equal to 3, sorry, not y to the power, y is equal to 3. So how then would we differentiate that? We say the differential of a constant going to result to 0. So we can clearly see that when it comes to y is equal to 3, it is also the same thing as what? Y is equal to what? 3x to the power 0. For any number to the power 0 is what? 1. So 1 multiplying to the same thing as 3. So once I have this, then I can go on to say that now I can differentiate. So I will say that differentiate y, differentiate x. That is for the y. And then for the x, all I will do is multiply what? 0 by 3. So we follow the power rule approach. So 0 multiplying 3, then x to the power 0, repeat and subtract 1 from it. You know, any number multiplying 3, multiplying 0 is what? 0. Any number multiplying 0 is what? 0. So generally, we will say that our dy over the x then is going to give us what? 0. This is the issue about differentiation of a constant what? Function. So once you see any constant function, it's a number, straight up it is 0. You don't waste your time generally at the end of the day. So let's take note of that. So that is the rule number 2, constant what function. Rule number 3. Let's talk about rule number 3, which is what? The differentiation of what? Sums and then different. Differentiation of sums and difference. So by sum and difference, I mean addition and subtraction. So sum and difference. Sum and difference. So let's take this a straight up NB that we need to have. We need to take note of this. That when it comes to sums and difference, all that we are saying here is that we are going to what? Differentiate the function term, very key. Differentiate the function term by term. Differentiate the function term by what? Term. Very, very important. Differentiate the function term by term generally at the end of the day. So how then do we go? Let's have an example to make meaning or bring home to what we are trying to talk about here generally at the end of the day. So let's say we have, for example, we are asked to differentiate the following function. So we have example. We have example. Differentiate the following. Differentiate the following functions. Differentiate the following functions. So one or I. We have first one, y is equal to what? 4a to the power 2 plus 3a minus 5. 4a squared plus 3a minus 5. Then let's add one more. Y is equal to 1 over 2. Y is equal to let's say x squared minus let's say 1 over 3 x plus 1. 1 over 3x plus 1. So now we have this function generally here. So now what is happening here? We are asked to differentiate this. So this is what we call sum and then difference. You just have to differentiate them term by what? Term. So we start with the first one. So we have our solution down here. Solution here. So first one, let's flow. So differential of y is going to give us what? Differentiate y, differentiate x. And what are we getting? So we flow with that. Differentiate y, differentiate what? X. Differentiate y, differentiate x. So we can say that when it comes to differential of y here, 4a squared, follow the normal power rule. 2 will multiply the coefficient of what? A, which is 4. So we multiply 2 by 4. Then repeat the whole of what? The independent variable, which is what? A squared. So we have what? A squared. And after that, we subtract 1 from what? The power. Right? Yeah. Then do same here. Here to the power is what? 1. Here to the power is what? 1. So what do? We multiply the 1 by 3, okay? And then we repeat a and then subtract 1 from the power. So we have what? 1 multiplying 3, okay? Plus 1 multiplying 3 plus what? Then we have, come on, I said plus. 1 multiplying 3, then we have what? A to the power 1 minus what? 1. And we said the differential of a constant is going to result to 0. So that one straight 0 in that case. So therefore, we'll say that our dy over the x is going to give us what? 8a, okay, plus 3. Remember, 1 minus 1 is going to give us what? 0. A number to the power 0 is what? A number to the power 0 is 1, actually. So 1 multiplying 3 is the same as 3. And then 0 is 0, so we don't bring that. So therefore, it's going to be our x differential 8a plus what? 3. I wanted to explain this to you before we move on. The derived function derived what? Coefficient. So this is what we call a derived what? Function. This is what we call a derived what? Function. This is what we call a derived what? Function. And this, right, is what we call a derived coefficient. So the coefficient generally at the end of the day. So coefficient. So derive what? Coefficient. So at any time you differentiate the function, you have any number in front of that variable, that becomes what? The derived coefficient at the end of the day. So let's take note of that. Let's take note of that. All right. So that is the issue here we are trying to present here. Okay, so that is with that. Then let's flow we are given what? Y to be equal to what? 1 over 2x squared minus 1 over 3x plus 1. So that we know differential of what? Sorry, here we're differentiating with respect to a. So you see, with my case, I'm even bringing x. It's supposed to be a, right? Not x. It's supposed to be a, not x. All right, so corrected. So we have the second one, y is equal to 1 over 2x squared. So let's flow. So here we have dy over the x to be equal to, so now let's see, differential of 1 over 2 is going to give me what? So here 2 multiply half, right? So we have 2 multiplying 1 over 2. Okay, 1 over 2. Then we repeat what? The independent variable with the s square. So with the square. So we have, then subtract 1 from here. I hope you are following. Then minus. Here the coefficient is what? 1 for the 1 over 3x. The coefficient of the x is 1. So the 1 will multiply 1 over 3. So we have what? That's what I'm talking about. 1 over 3. So 1 multiplying 1 over 3. Then we have x to the power 1 minus 1. Differential of a constant, we said is what? Is 0. So you can write that or you can ignore generally at the end of the day. So therefore, what are we getting? We have our dy over the x to be equal to the half will cancel the 2. So we are left with what? X. And remember, when you subtract 1 from 2, it is going to be what? 1. So x to the power is the same as x generally, right? Then minus here 2. What is happening here? I'm going to get what? 1 over 3. Remember, here is going to give me 0. 1 minus 1 is 0. So 0. In number to the power 0 is what? 1, right? So it's minus 1 over 3 and here 0. So therefore, this is going to be our derived what? Function generally at the end of the day. So that is the sum and what? The difference. Rule number 4. 4, we go. Rule number 4. So rule number 4, let's see. So rule number 4 is also talking about, let's see the rule number 4 here. Let me check my slide. Rule number 4, how we differentiate what? Exponential function. How do we go? So stay with me carefully here as we unravel this. So exponential function. Exponential function. Exponential function. So how do we differentiate an exponential function generally at the end of the day? Exponential function. Now let's see. Exponential function. So a function has an exponent where we have the function in the form of this. So we have, let me bring her here. So exponential function, we have a function of this form. Say y to be equal to what? The exponential. So more that I can check this on your calculator. It's more like a slight e or a slight e. It's on your calculator, you can check. All right. So let's say y is equal to the exponential function. Let's say a function like we have f of what? X. As we started, or as we, when we begin this lecture, we said that f of x is the same thing as y. Okay, so as soon as I see f of x, you can represent that as what? As y. So you don't actually confuse yourself with that. So this is how exponential function actually looks like. So how then would you differentiate an exponential function? That is the goal here. So let me bring it down so that we actually narrow it down to explain. So we have what? Exponential function here. So to differentiate exponential function, since we are differentiating that with respect to what? X in this particular case, it is going to what? It is going to be differentiate y, differentiate x. That is the on the y side, that one we know. So it's a done deal. But when it comes to the exponential part, all that we're going to do here is that we are going to what? Differentiate the function on top of this what? Exponent. We are going to differentiate the function on top of this exponent. Once we are done with that differential, whatever we get as what? A derived what? Derived function. We use that derived function to come and multiply if there is any coefficient number in front of the exponent. Okay, and after that we repeat the whole of what? The exponential function. The same thing as the power rule, everything. So first we have to differentiate what? The function on top of the exponent. So it becomes what? Let me bring this. It becomes what? F prime of what? X. it becomes f prime of what? X. So let me bring in this. We will get there when we get to higher derivative, but for now, we just have to have this idea. When we talk about f prime of x, it's the same thing as what? The first differential, which is what? Dy over what? Dx. When we have f double prime of x, it's the same thing as what? D squared y over what? Dx squared, generally at the end of the day. So what is then happening here is that at the same time you see f prime with the same thing as what? Dy over dx. So you don't bother yourself so much with that. So we differentiate what? The function here, okay, and we are getting what? F prime of x. After I use the f prime of x to multiply if there is any coefficient in front of the e. If there is none, no big deal, just have to bring it down. So once we differentiate, we use that to multiply what? The coefficient. So let's say here the coefficient is 1, so we just have to bring the multiplying what? 1. And after we repeat the whole of what? The exponential function is going to give us what? Our exponential function, and we have the function on top of it. This is how we differentiate an exponential function. So let's make meaning out of this by bringing an example. I think with that way, you will be able to appreciate this better. So let's bring in an example to clarify this. So example. Let's say we have what? Function y is equal to 4 with as an exponential function 3x plus what? 2. You realize that you are seeing 3x plus 2. It takes you back to our rule number 3, sums and difference. So it is a sum. So you differentiate them term by term before you can deal with the multiplication of any coefficient of the exponent generally at the end of the day. Hope that is clear. All right. So if that is the case, then we can say that, okay, we have our solution here. So here we're differentiating with respect to what? X. We are differentiating y with respect to x. So we have dy over what? Dx. Okay, and that should give us what? So we come back and differentiate what? 3x plus 2, term by term. At this point, you should know how to differentiate within the fastest possible, right? Or fastest time as possible. I mean, generally, that's what I'm trying to put across here. So differential of 3x should give you what? 3. Because here is 1, the power x is 1, multiplying 3, and we subtract 1 from the x, we are getting 0. So here, I'm going to say the differential of 3 is going to give me what? 3. Okay? Once I get a 3, we also know the differential of constant is what? 0. So that one, we don't bring that into the scene. So once we differentiate the function, we then use the function to multiply any coefficient of the exponent. So we have coefficient 4 there. So 3 multiplying what? 4. So once we are done, we then have to repeat the whole of what? The exponential function. The exponential function. The exponential function, and not together with the coefficient, because the coefficient is already captured here. So that's going to give us the exponential function 3x plus what? 2. So therefore, we have our dy over the x to give us what? 12 with the exponential function 3x plus what? 2. And we are done. And this is how we also differentiate what? An exponential function. So let's take note of that. I mean, all exponential function at the end of the day. So let's take note of that. If you have any question, you can drop in the comment section so that we'll bring it up and see how far we can. So okay, I see some charts coming in here. Let's see how far we can look at that. This is please the sound. Okay, I think I'll fix that, so don't worry. Okay, that's fine. All right. So let's continue. So that is the exponential function. So rule number 5. Now let's move on to rule number 5. Rule number 5. Let's talk about rule number 5, which is what? Differentiation of what? A logarithm what function. So you are talking about logarithm function. Log function. So logarithm function or functions. How do we differentiate any log function? How do we differentiate any log function? That is what we need to understand generally. If you're online, do want to share the video so that others will get a benefit to join. If you haven't liked, to like the video as well to get more engaged. All right. So how do we then differentiate what logarithm function generally at the end of the day? So when it comes to differential of logarithm function, this is also actually come into the scene. Differential of log function. By convention, log can also be written as what? LOG in the form of shortcut log. or ln as log, but most of the time I prefer using the ln because that is the shortest way to go, right? So log function is also in the form of what? Say y or f of x, right? I'm coming. Say y is equal to, so the log going to be attached to the function. So we have what? Let's say ln as the log attached to the function f of x, generally at the end of the day. So at any time you see any function with a log attached to it, it is a log what function. It is a log what function. Generally at the end of the day, it's a log function. So how then do we differentiate a log function? Let's see how it goes. Generally at the end of the day, let's see how it goes. So if you have a log function like y is equal to ln, which is a log of a function f of x, it's pretty simple. To differentiate this function is very simple. All that you want to do is differentiate the function given in the question. After that, you divide the result by the original function, and that will get rid of the log, and we get the differential of a log function. So let's make meaning out of this. So here we're going to what? Differentiate y, differentiate x. And what is happening here? Now you come and differentiate what the function. We said the differential of f of x is going to be, for the first time, going to be what? F prime of x. So we're going to have what? F prime of x. But once you are done with that, you then have to differentiate. As a differentiate, you then have to divide the derived function, right, by the original function is what? The f of x. And once we do that, that will be able to help us to get rid of what? The log function. And that is that. Let's make meaning of this by introducing an example. So example, I think with that will be okay. We are asked to differentiate this function. Y is equal to, in this case, y is equal to our log function 3x squared plus 2x minus 1. So these are log function that we have been given. How then do we differentiate this function generally? So let's have our solution down here. So we said that to differentiate this function, this is what we're going to do, right? We're going to say that differential of what is going to give us what? Dy over dx, right? And we come back to the log part. So you see that there's actually what? Sums and difference happening here. So we're going to differentiate them term by what? Term. So differential of 3x squared should give you what? At this point, you should be able to know. A differential of 3x squared should give you what? 6x. Because the 2 multiply the 3, subtract 1 from the 2. So it's going to give me what? 6x. Then differential of 2 is going to give me 2. Differential of 1 is 0. So don't bring that into the scene, right? So once you have done with that, all I want to do is to also divide the derived function by the original function is what? 3x squared plus 2x minus 1. And that will help us to differentiate what? The log function. That will be able to help us to differentiate what? The log function generally at the end of the day. So let's take note of that. Let's take note of that. If you have any question, you can drop in the chat box. So we'll take it from there generally at the end of the day. Okay, so that is what we need to understand. Give me a sec. Let me check out this so that we continue in that case. So we continue in that case. I'm coming. Check out this. Check out this. Check out this. So let's continue. Let's continue generally. All right. Just have to sort out one or two things, right? So let's go. So that is the issue about what? Differential of what? A log what function. Differential of a log function generally. So that is fifth rule. Now let's move on to sixth rule. Rule number 6. So rule number 6. Talk about what? Product what? Product rule or product functions. So product functions. Differential of what? A product what? Functions. How do you differentiate a product function generally at the end of the day? So let's go. So when it comes to differential of the product function, I say production, product function generally, right? So when it comes to differential of what? A product function, you're saying that two or more functions are said to be product where the functions are multiplying or they are combined. By combination means that you are multiplying it all together, right? That's what a product. So let's build up this knowledge. Let's say y is a product of what? Two functions, say u and then v. Okay, let's say y is a product of two functions, u and v, and u and v is also a function of what? X. Follow carefully. Let's say y is a product of two functions, u, v, and u and v is also a function of what? X. So from this deduction, therefore, we can say that y should also be equal to what? X. I hope you agree with me. If y is equal to uv and uv is also equal to x, then we can also conclude that then y should also be equal to what? X. So that is the first state that we built general identity. So if that is the case, that is fine. The next thing we want to do here is that we don't have to bring this down. So let's bring it down. So we have what? Y to be equal to what? uv. Okay. And let's say we have the second one is u and v is also equal to what? X. Let me bring it up here. We have some space for some working. So just follow carefully. X. Then we also conclude that then our y should also be equal to what? X. So now let's follow carefully here. Let's see what is happening here. We want to differentiate what? This function. This is a product of two functions. So the first thing we want to do is to start with what? U is equal to what? X. Now when it comes to differential of product function, this is how it works. You see here, I'm having two functions here, or two terms here, which are the functions, which is u and then v. So for me to differentiate these functions, which is being combined as a product, I want to first differentiate what the u. So what I will do is saying that differential of u, right? If I want to differentiate u, I'll make sure that this is not part of the differential. So I'll hold this v. So what I will do here is that I'm differentiating what u with respect to what x. So it becomes what? Differentiate what? It becomes what? Differentiate u, differentiate what? X. Because I'm differentiating u with respect to what? X. So I'll hold the v and I'll differentiate u with respect to x. So that is the differential of u with x. But since I hold the v will come and multiply the u over dx. So it becomes what? Multiplying what? Du over dx. So that is the first part. Remember, when it comes to differential product functions, it's always going to result what? An addition. Differential products are going to result in addition. So once I differentiate the u and I attach the v to it, I'll come and do same, and I'll say that plus. Then I'll hold what? The u, and I'll differentiate the v also with respect to what? X. So also becomes what? Differentiate v, differentiate what? U. And I'll attach the u as a product multiplying to it. Okay? So once I'm able to get this, that is the final. So when it comes to product function, you hold one function, you differentiate toward the other. And you say plus, and you come back and hold the one that you hold initially, and then you differentiate that one together with the one you differentiated earlier, right? So that should be equal to, sorry. So that should be equal to our x. But remember also the differential of x is going to give me what? 1. Differential of x, right? It has a power of what? 1. So 1 will multiply the x here, so it becomes 1. And we have x to the power, so subtract 1 from the power and we get 0. So a number to the power 0 is 1. So also differential of x is going to give me what? 1. So that is the first one. I'll have first equation here. I hope you are following. So the first is going to be established. Du over ds v plus dv over du u is equal to 1, because that is the differential of x. So this is the first part. And then let me try to bring this one here so that will make meaning, the blue one. So we also have, let me bring it up here. So we also have, we said that y should also be equal to what? X. So now I want to differentiate y with respect to x. So here I will say that differentiate y, differentiate x, and that should be equal to, you also know the differential of x going to give me what? 1. So I have 1 here, equation 2. Now follow carefully. We said that if y is a function of u and v, or the product of u and v, that is here. Now where is our u and v? Now we know that this is our u and v, right? We know that this is our u and v. It stands for this. So this is our u and v. This is our u and v. Okay, and we also know that our y, please also know that our y, the differential is also this. I hope you are following. So what is happening here? You just want to come back and substitute all these things into this equation where y is equal to u v. So in simple, we are saying that we have 1 here, we have 1 here. So for equation 1, we have this and it's equal to 1. And for equation 2, we also have the whatever it is also equal to 1. So can we equate the 1 output here for this and this? Can we equate the 2? Can we equate these 2? It's possible we can equate, because this is 1, this is also 1. So that would then mean that, therefore, our dy over dx, follow carefully, therefore, our dy over dx should give us what? Coming. Therefore, our dy over dx should give us what? But we know here is 1 here, so we're going to equate the 2. It will give us what? Du over dx v plus dv over du u. And this is what establishes what we call our product rule or product differential. But since you have a product of two functions, this is how we differentiate it. So all that you, for your table, all that you're going to do is to say that you're going to make a representation. Let one represent u, let one represent what v, and then you differentiate them as such. That's very simple. So this is how we derived what the product function for differential. So let's take note of that. It's very, very important that you know that going forward, generally at the end of the day. Okay, so if that is the case, now let's take an example. Let's make meaning out of what we are trying to talk about, because without that, it makes this formula vague without better understand. So let's bring home with an example. So let's say we have example. So let me bring up this example. So it is out of our product function that we can try to merge up more than one rule that we have discussed already. So we can bring in like exponential function, log function together as one. You can also bring in like what, sum and product. Sum and then differences. And what I'm trying to say here is that we can bring on board different rules that we have discussed together as one to form what, a product, and you will be required to differentiate them. It's simple, it's not difficult. Once you know, oh come on, once you know the approach to differentiate individual terms is the same they're going to use to do generally here. So let's take an example to make meaning. So example 1, we have y to be equal to x squared plus 1, multiply another one, which is what? X, like say 3x plus 2. Now let's bring in the same variable so that you appreciate, so that I'll add in the other variables that you need to know. So we are asked to differentiate this. How do we go by the differential of this? It's very simple. All I want to do is to say that now we are differentiating with respect to what? X. So dy over dx will be equal to, here we have two approaches. I'll present the two and then you decide which one will best suit your understanding generally at the end of the day. So all I want to do here is to say that now these are the products of two functions. So our first word, hold what? The second one is what? 3x plus 2. Now differentiate what? The first one is x squared plus 1. Notwithstanding, you also see in what? Sums and differences here. So this is a sum of two expressions. Likewise, also here sum. So you're going to differentiate them term by term before you can even apply the product rule here and there. So stay carefully here with me so that we unravel this generally. So I will hold this 3x plus 2 and differentiate what x squared. So let's look. So now the differential of x squared is going to give me what? 2x, right? Differential of 1 is a constant. So it's going to result to what? 0. So we don't bring that. And then we attach this to it, which is what? 3x plus what? 2. And we said that product rule always results to what? Addition in terms of differentiation. So we say plus, okay? And then we come back. We differentiated what? X squared plus 1, and then we held this 3x plus 2, and now we are multiplying the differential or the derivative of the first one by what we held generally. So if that is the case, the next thing we want to do, we're going to say that plus, then we come back and hold what? The x squared plus 1 and differentiate what? 3x plus what? 2. So that's going to be what? So we're going to have here to be x squared plus 1, okay? X squared plus 1, then we differentiate 3x plus 2. So differential of 3 is going to give me what? 3. I think at this time you should know that it's 3, right? Yeah, so it should be 3. Differential of 2 is a constant. That's going to result to what? 0. So we don't bring in that. So 0. So it's going to be like this. So we therefore have to say that dy over the x is going to give me, so we can expand this, right? So 2x multiplying 3 is going to get what? 6x squared plus 2x multiplying 2, we are going to get what? 4x. Then we say plus. Then we can also expand this. So 3 multiplying x squared, we can get what? 3x squared plus 3 multiplying 1, we can get what? 3. So once you're able to get it, then you then have to arrange this in a form of what? A quadratic in ascending, in the form of polynomial in ascending order of what? Their degree. Okay, so you say that dy over the x should give you, so now let's see, we add like terms generally at the end of the algebraic expression, we add like terms. So 6x squared plus 3x squared, what are we getting? So we are getting what? 9x squared, right? And then we have what? Plus 4x. Then we have what? Plus what? 3. If by any means the quadratic that you get, you can factorize it in the simplest form, it's advisable that you factorize it, because in the examination condition, you might not see this as, let's say, 9 squared plus 4x plus 3. If it is possible that they can factorize, they will factorize it and have it there. So you see that I've worked this, but I'm not seeing this. What is happening? You just have to go further and then do factorization to see if it actually meets what they have provided generally at the end of the day. So this is what we need to understand when it comes to the product rule. So that's the first approach. The second approach you want to do is to go by the derivation of the formula that we have used. So alternative method, you are going to say that you have what? Your y to be equal to what? X squared plus 1. Then we have here to be 3x plus 2. I hope you are following. All right. So what you're going to do here is to say that we know from the product rule that we can say that let y be equal to u and then v generally here. So what I will say here is that, okay, if that is the case, I will say that let u be equal to what? X squared plus 1. That's the first thing they want to do. And then also let v also be equal to what? 3x plus what? 2 in order, in sequence, because u come before what? V. That's why you have u and then v generally here. So that is the first, and then after I make the representation, after you have made the representation, the next you want to do is to differentiate them individually. So now we differentiate u with respect to x squared plus 1. Okay, so we have what? Differentiate u, differentiate x, and we're going to have here to what? 2x. Or we can see that, and differential of a constant is going to result to 0. So that one is out of what? The issue here. Then we come to next one, differential of what? V with respect to x. So we have what? Differentiate v, differentiate what? X. And what are we getting? What are we getting here? We can say that here we are getting what? 3. So once you are done with the individual differentiation, you will come back and then quote your formula that we know that our dy over dx for the product rule is what? The what? Let's see. Is what? Du over the x. It is what? Du over the x over the x, then multiplying v plus dv over the x multiplying what? U. And that will give us our product what? Function derivative. So all I want to do to come back and do your substitution, and that's it. Okay, so now let's flow. So we know that our du, the x is what? 2x. So we have that here, 2x plus, sorry, as a plus, we have v also here. What is our function? V is what? 3x plus 2. So we multiply that by what? 3x plus what? 2. Then bring in your addition here. What is the v over the s is what? The v over the s is what? 3. Also multiplying u, which is what? S squared plus 1. How we can see similar thing here? Oh, I wish I can see. How we can see that? Oh, you can see. But yeah, the same thing, right? Generally. Next one, look at this. Right? And what we also had here. So the same thing. So at the end of the day, the two are actually going to give you the same result. And then you just have to work it out, simplify it, and then break it down. So once we get here, it's the same thing as this. It follows you to get to the final answer, which is this. How we can say that? Yeah, so that is what we need to when it comes to the product rule. Okay, product rule, product rule, product rule. So as I said, the examiner can actually what combine two rules together and ask you to differentiate. You must master the calculus. Once you know how we differentiate each individual, all that you want to do, differentiate them individually. After that, you apply your product rule. You hold the first one, let's say you hold the second one, you differentiate the first one, and you come back and say plus, and come and hold the first one, you differentiate the second one. That's it. Or use the rule that we have described here. Make a representation, different term by term, and then quote your formula. dy over ds equal to what? Du over dsv plus dv over du what? U. That's it. Simple. Right. So that is our rule number what? Rule number 6. So let's build up one last rule and then we get our wins out of this platform. So rule number 7 is what we call the quotient rule. The quotient rule or the division rule. Quotient rule. The quotient rule of differentiation, or let's say the quotient functions generally. Quotient functions. Quotient functions. So how do we then differentiate quotient? So follow carefully. Follow the same logic that we use to derive the product rule. But just that here it's going to result in division generally here. So now follow carefully and let's see how we go. Let's see how we go. Follow carefully and let's see how we go. So now let's see. Let's say we have what? Two functions. We have two functions where y is equal to what? Y is equal to what? U over v. Right? And then u over v is also a function of what? X. Then we can conclude that let what? Y also be equal to what? X, as we use in the case of product function. Are you following? Right. So the next thing you want to do is that once you make this representation, the next thing you want to do is to what? Go back to differentiate what? These what? Functions that we are bringing on board here. So what is the next thing we ask ourselves? We'll come back to what? The second word equation, which is u over v is equal to x. So we take them like that and differentiate. Now, if you want to differentiate this using even the same product rule approach, you can still do it. It's very simple to go. So all that you want to do is to write what u over v is equal to x in a linear form or in a horizontal form. What do I mean by horizontal? We are going to ensure that the v joins the u at the top here. So that means that if I have 1 over 2, I can write this as 2 to the power negative 1. I hope you believe that. I hope you understand that we can write this as such. If I have what? 1 over 3, I can write this as what? 3 to the power negative 1. If I have 1 over 2 to the power 2, I can write it as 2 to the power negative 2. So let's flow. So that is what we are trying to build up here. So that means that here, if I have u over v, I can also write u over v is equal to x in this form. So I can say that my u over v, which is equal to x, can also be written as what? U multiplying what? V to the power negative 1, and that should be equal to what? X. I hope you are following that. Okay, so if that is the case, then we'll then come back to our product rule, because now these are our product of two functions, just that we have one on top as what? An exponent of negative 1. So we come back to our product what? Rule. So now let's see how it goes with that. So now I'll hold the second, which is what? V to the power negative 1. I'll differentiate u with respect to what? X. Okay, so I'll have here to be du over what? The x. Follow me carefully. That's the differential of u with respect to x. And I'll bring in v to the power negative 1 to attach to it. So we have what? Dot v to the power negative 1. So that is the first part. I'm done. Now I'll say plus, because it's a product of two functions, because I've converted from a division to what? A product. So now we follow that rule. Then I will then have to differentiate what? V to the power negative 1. So how then I go by this? We said that the normal differentiation for power rule is that, first of all, you differentiate the power, you differentiate what? The individual variable, and then subtract 1 from what? The power. I hope you remember that. So that's what we're going to use here generally at the end of the day. So let's take note of that. So how then do we go by this? So I'll first of all differentiate the power. So the power will come back and multiply the coefficient of the v, which is what? U. So we have what? Negative 1 multiplying u. Okay. And then I will repeat what? The whole of what? V to the power negative 1. I hope you are following. I repeat the whole of v to the power negative 1, which is v to the power negative 1. And I'll subtract 1 from the power again. Because that is a rule for differentiation. You subtract 1 from the power. Okay, so once you are done with that, you then have to differentiate the v itself as, let's say, a variable with respect to what? X. So that becomes what? Dv over what? Dx. That becomes what? Dv over what? Dx. Let me repeat it again. First, you have to what? After you are done with the first one, the second one to do is that you differentiate the power negative 1. So the negative power will multiply the u here. Okay, and after that, you repeat the whole of what? V to the power negative 1. You subtract 1 from it. But even before you do that, you must also differentiate what? The v as a single variable with respect to x. And that's what we have done here. Because you know that multiplications are commutative. So when we change their position, still we are going to get the same result. That's why you are still getting the same result. So after you have differentiated the power, and you differentiate the variable as a single variable with respect to the other independent variable. After that, you then have to repeat the variable with the power and subtract 1 from the power again. So we have this established generally. And you know that differential of x is going to give me what? 1. So let me bring in that here so that we know that we are done with that. So therefore, I can say that the u over ds multiplying v to the power is the same thing as what? The u over the x. For now, let's maintain this v to the power of what? Negative 1. You know that when negative and positive meet, we have what? Negative, right? So that's going to give me what? Negative u v. Remember, here, negative 1, negative 1 are going to fetch me what? Negative 2. All right. Then I have what? My dv over what? Dx. And that's equal to what? 1. Now let's flow. So now we can rewrite it in a more better way. So we have du over the x. Remember, v to the power negative 1 is the same thing as 1 over v. Why we were having 1 over v, we said it should be what? V to the power negative. So we are now bringing it back to its original state. So follow carefully. So we can say that here it is out of what? V. Or the same thing as what? V to the power negative 1 as we were having initially. Then minus. Here too we have what? U. Okay. Or let me bring in this one. So let's say we have what? dv over what? The x multiplying what? U. And remember the v to the power negative can also be written as what? 1 over what? 1 over what? V squared. But when you want to write in a more horizontal form, that's where we have what? V to the power negative 2. I hope you are following that. All right. So if that is the case, if you have any question, you can drop it in the chat so that we take it from there. So if that is the case, then what do? We bring in here 2 as what? Our v square, and that should be equal to what? 1. Follow carefully. So now what is happening here? We have what? 2 divisions and 2 terms here. So we just have to find the LCM. So what is the LCM of v and v square? It's v square at the end of the day. So v go to v square what? V. So v will come and multiply du over dx. So we have what? Du over dx multiplying what? V minus. Then v square also go to v square how many times? 1. Multiplying the v over the x u. So it becomes what? The v over the x, and we have what? U. And that is equal to what? 1. So that is the second aspect of the equation that we have differentiated. Then we'll come back and ask ourselves that we also know that differential of this, which is what? Y to the power x, is the same thing as y is equal to x rather, not y to the power x. It's the same thing as what? The y over the x, and that should be equal to 1, right? Yeah. So now we have first equation here, second equation. So now we can equate the 1 together. So therefore, I will say that my dy over the x should give me, as the first equation, should be equated to what? The second one, which is what? Du over the x v minus the v over what? The x u, okay, all divided by what? V square, all divided by v square. And this is what we refer to as the quotient rule. This is how it was what actually established. That's why in most tests you see the quotient rule for differential is what? Du dx multiplying v minus dv dx multiplying u, all by v square. This is how it was derived. So let's take note of that generally at the end of the day. So if you have any question on this, you can't go by this whole approach, convert to a product function and differentiate, you're going to get the same result. Or better still, go as a second formula where you represent what? The u and v with the function given and differentiate them individually. After that, you quote your formula and boom, you are good to what? Go. So that is the idea about differentiation with respect to this aspect that we want to understand generally at the end of the day. So I would like to end here. So if you have any question, you can drop in the chat for us to take it on generally. Right. So thank you so much. If today is your first time on the channel or you have been here since, well, thank you so much for joining us from the beginning of this channel. But do all to share this video. That is my humble plea. Share this video because a lot need this so that they can understand everything perfectly. Please share this video, subscribe to the channel as well for me, and like it as well. Please share for me. That is the only thing I'm asking for you. You just share for me. Just share for me at the end of the day. Thank you so much for joining us today on this channel. You're always grateful having you here. So we'll come your way, hopefully, from tomorrow going, right? So the link will be shared on the page if you had to go live so that you can join us quickly on that case. So thank you so much for joining us. I will see you in the next section and have a great week. Bye-bye. Okay, before let me check this. I think there was one comment up here. Who is that? Okay, Joseph is saying that. Let's see. Thanks very much. I now understood the product. Okay, that's fine. Right, that's great. All right, so that is that. Thank you, and I will see you in the next section. Bye-bye.